General relativity, step by step. Back in CSS 025, I derived two equations from the Einstein field equations for our co-moving coordinate system. And I observed that we had two equations and three unknowns, and so I needed another piece of information to close the system, and that piece of information was the equation of state, which I'm going to use in this and subsequent screencast, and the subsequent screencast. Okay, so what were those equations? We got a double dots over a plus 2a dot over a squared plus or minus 2 over r0 squared a squared equals cosmological constant minus 4 pi g, let's just get this right, rho 0 minus p0, rho 0 minus p0. I don't want to crowd my writing too. And the other one was 3a double dots over a equals cosmological constant plus 4 pi g rho 0 plus 3p0. Is that right? Yes. No, that's a minus and that's a plus. So it's easy to get these things wrong. Just a minute. That's a dots that's the plus term and that's the minus term. Yes. It's easy to get those things wrong because they're both the same multiplier, and it's easy to write them in the wrong direction. And it doesn't take a genius to figure out what I'm going to do. All I'm going to do is to multiply this guy by 3 to cancel out the a double dots, and I'll be left with a simpler equation for a dot, which is nice and easy to deal with. So I'm just going to multiply this guy by 3. That 2 turns into a 6. That 2 turns into a 6. That's 3, and now we've got 12 pi g. 12 pi g. And I'm just going to subtract one from the other. Let's pinch in a little tiny bit. So we've got 6a dot over a squared plus or minus 6 over r0 squared a squared equals, this one minus this one is 2 lambda plus, now the pressures cancel because I've got minus p0 and I'm subtracting another, sorry, I've got minus 12 pi g p0, minus 4 3s are 12, so the p's cancel. And what about the rho 0 term? Well, I've got 12 minus minus 4, which is plus 16 pi g rho 0. Well, that's nice, and I guess I'm going to cancel by a factor of 2, and I'm going to start fooling around with various terms here. So actually I'm going to cancel by a factor of 6. So we've got a dot squared. What I'm going to do is I'm going to multiply this equation by a squared over 6. That's what I'm going to do. Plus or minus 1 over r0 squared equals, and then divide by 6 and multiply by a squared times over 3 plus 8 pi g rho 0 upon 3. Is that right? Now what I'm going to do is some slight rearranging. I'm going to take this and put it on that side, and I'm going to take this term here and put it on that side. Nothing very difficult there. So a dot squared minus plus 8 pi g rho 0 over 3 equals minus or plus 1 over r0 squared. You'll remember that r0 was the radius of the universe. It's usual to call this k, where we've absorbed the sign into k, which is quite nice. And then I'm just going to do a little bit of fiddling with this. Minus, oh, there's an a squared. It's easy to forget that. Yes, I've forgotten the a squared there. Minus. Now then, let's get this right. We've got a squared times 8 pi g over 3 into rho 0 plus cosmological constant over 8 pi g, which equals k. So it's a dot squared minus 8 pi g over 3 into rho 0 plus rho vacuum times a squared equals k. And now what I'm going to do is I'm going to rewrite row 0, which is just the density, I'm going to decompose it into its two forms. Again, this is not really mathematics. This is more a sort of physical convenience, and we'll see in a minute why we need to do this. So we've got row 0 is the density in the material's rest frame. So we've got row, I'm going to call it matter, plus row radiation, plus row vacuum, all times a squared equals k. And this is called the Friedmann equation. Now it looks as if we can just solve this, but we can't, because the various rows are functions of time. And what we're going to need is to make that function of time explicit, and then we're going to be able to solve this equation. So there it is, and I'm going to stop there. Stop.